Yo, it's your boy, Holden Larson, with another class of pre-calc, 4th period, March 22nd. Action.
This is how fast the video plays.
Did you leave that in the video for yesterday?
Yeah. People have seen the editors. Alright. Okay, hey, you need to have your notes out, please. We're going to talk about the law of cosine today. I want to talk about the last case, do a couple examples of it today, and then we have brand new topics today.
What a cheat sheet. I need that.
Cheat sheet, yes. Have your cheat sheet out.
So I can use that as my notes.
Yep. Are you going to have it out with your notes?
I wrote my notes on it.
Try not to do that. Okay.
I just do like examples on it.
Hey, let's go. We have a lot of notes to cover. I have a little bit of time to do it. So let's go. Okay. Hey, tomorrow. Hey, tomorrow, just kind of fill you in. We're going to be continuing with the law of sine, law of cosine type of material. But the fun part is about tomorrow, we're going to kind of do a little activity tomorrow that's a lot different than what we normally do, where we do notes, homework, and whatnot. This is going to kind of fill in as our homework score tomorrow, where it's, I think you guys are going to really enjoy it. It mixes a little bit of history, it mixes a little bit of actual math involved, and so it's definitely different activity than you've seen before. So take a seat.
Today?
So
Hey, where?
that's tomorrow. Because we have more time tomorrow to actually get through. So sit. Okay, all right, here we go. You need to have your notes up, please. We're going to go through it. All right. As I warned you today, we're doing the law of cosine, law of sine.
Double heavy.
All right. Hey, law of cosine. Yesterday we showed where the formula actually came from. The goal today is to do an example or two of it to make sure that you know how it works. So the example will be just that set one where we're going to be using side angle side, the side angle side postulate to show us how to actually solve it. Then the goal today is we have a brand new type of problem where the new problem that we have to look at is using the SSS postulate, which is side, side, side. That's the one we haven't done yet, because it was the one that we said that we couldn't solve it yet. We're going to look at that today. I'm not going to go through the whole way of how they came up with the formula and whatnot. I'm just going to give you the formula, walk through it, and hopefully it makes sense to you. Now, goal today, after we get through these, we have a brand new topic today, which is something you definitely need for the activity we're going to do tomorrow. It's called directional bearing. So you want to write that word down, directional bearing.
So what exactly are we doing tomorrow? I heard you say that it's going to be fun.
Yeah, it's a fun little activity. It mixes history, it mixes a little bit of math.
Is it history?
We watch a video. You're going to like it. It's pretty cool.
But is it involving pyramids?
No.
Wait, do we get ice cream?
No. To show
But
that
we're going to like it, and there's no pyramids, there's no ice cream.
you're not. It's pretty cool. So,
What is left to be enjoyable?
you'll see. All right. Now, let's go right into our example stage. We have about 25 minutes left here.
The SAS just a review thing, right?
Yeah. All right. This first problem, this first example, where we're doing the SAS postulate. This is a review that we did yesterday. I want to just kind of walk you through the steps, actually do examples where we actually do calculations, because we didn't do that a lot yesterday. Yesterday was just talk about where the formula comes from. So,
What's the lockdown procedure?
okay, we'll get to that. I don't want to put that on here.
Yeah, then you put it on YouTube, then the criminals know what we're trying to do.
Exactly.
Never tell the criminal.
Hey,
We have guns. Criminals the boss.
okay. Alright, so SAS postulate. Let's walk through an example of how to solve it. This is a traditional problem where they give us walls, they give us an angle. Let's say this angle is 63 degrees. Let's go with a 17 and let's go with a 26. Yeah, let's go 26. Alright. Alright, so let's say that these are my walls. Again, pictured not done on scale, it's my generic picture I always show you. When you have this set up, the law of cosine is used because what we do is we find the opposite wall. So we call this little b. That's what it's used for. That's how I remember it. It looks like the Pythagorean theorem, but it has one extra piece added onto it. It's actually subtracted on it. So here's how it works. The wall you're trying to find squared is equal to the other two squared added together. So that's the 17 and the 26. So it does look like the Pythagorean theorem. Even though it's not a right triangle, doesn't have to be. So that's the setup. Now, the extra part we're going to subtract on is this piece. So the extra part that you put on like the Pythagorean theorem looking part, it's minus 2 times the two walls cosine the angle that's in between them. That's just how it's always set up. And so it looks like the Pythagorean theorem with one extra piece. That's my shortcut for how I remember how to do these problems.
It's always minus 2.
It's always minus 2 times the two walls times the angle that's in between the two walls. And that helps you find the third wall. Now this is our normal examples we usually do. Because if it's any other setup other than this, you could use law of sine to just do your proportions. But when it's this setup where it's SAS, you have to kind of do the law of cosine. There's not another way to do it other than doing the old school of like drawing right triangles, and it would be a nightmare. So I don't want to do that.
I think the old school way is kind of fun.
Okay. Huh? We could do that. All right. Let's kind of walk through this. This is the part where we do need calculators today because we are going to do actual calculations with decimals. I know a lot of people wanted to do that yesterday. But yesterday was talk about where the formula comes from. Now we're going to actually do the calculations. So I'm going to take out my calculator here. If you guys have yours out, you want to try to type some of this in to make sure you know where the numbers are coming from.
No Casios.
You can use whatever type you want as long as you have some of the scientific keys. Okay, 17 squared should be a 289.
I'll check.
Should be a 289. 26 squared, I think it's a 250 or 576, I think. 26 squared. 676. 676 minus, now we're going to take 2 times 17 times 26. 2 times 17 times 26 is an 884. Cosine 63.
401.32.
Okay.
Negative.
Now, here's the big thing that we need to make sure of before we move on to the next part. Hopefully everyone's getting those right numbers that I've been typing. When I do my problems, you'll see me exactly do this step, where I find each number separately. I'm going very slow, I'm not just typing it all at once and hitting enter. I know your calculators can do that. But I want to guarantee to show you where some of these numbers are coming from. The one part I'm actually worried about is this part. The reason being I'm worried about the back. That's one item back there. We're subtracting, 884 times cosine of 63. If this number here is obtuse, let's say, instead of a 63, let's say it was like 103, the problem is with doing an obtuse angle is cosine will give you a negative number on a calculator. And if you have a negative number sitting here, and you take it times a negative 884,
That's a positive.
it's positive, and some people wouldn't write that. Because they type this in, they type just this, and they go, oh, it's negative. So yeah, so they're subtracting whatever that number is, but they don't write the negative again. It's negative. For mine, I don't need to worry about it. This cosine of 63, it's in the first quadrant, it's a positive number. Positive times 884 is a number, and then we're going to subtract whatever that is. It's not going to turn out to be negative where I have a double negative and making it positive. So, say it again?
401.3276018.
307?
Point. No.
76314.
327.
327, sorry.
601.
Okay, 327. I'll go 3 decimal places. We're subtracting that number, the 289, the 676. Now that we're here, we have all these numbers written down correctly.
That's 965.
Okay, all right. We have to add or subtract. I want to go all the way across. I don't need to worry about getting negative or positives. I don't really care about that. I know that the answer is going to be positive in the end because we're adding some big numbers here when subtracting very small number.
6.6.
Yeah, 924.673. And then the last step is to take the square root of that number. That's the part that people will forget. They forget it's b squared, and to get rid of the square, you have to take the square root. So this answer, whatever this is, 673, whatever that number is, try to go about 3 decimal places. I know we're not going to be super exact because we are rounding each time we get to a new number. But the actual square root of 924.673, 30.41. 30.408 if I want to go 3 decimal places.
That's not.
Yeah, you,
So,
if you do, because adding those and subtracting that is not 2.
I feel like all the teachers.
It is 500.
oh, I put the decimal in the wrong spot. Oh no.
Oh, Mr. Ward! You are throwing us off. Oh my goodness, Mr. Ward.
Grade
Oh
9,
my
676. I subtracted 40.1. That was silly.
How are we expected to get
Oh,
correct
yeah.
answers? How about 23.7417858?
Guys, 7858. Please, 23.
I got 7 Ward.
Okay, well,
She didn't get that read. All I know is he didn't have the right one.
alright. 5, 6, 3.
How about 23.7417958?
Square roots. Did I write it down wrong again? Don't tell me that.
I don't know.
7417958.
Alright, hopefully that's the number everyone's roughly getting. Alright, again, apologies. I didn't realize I had the decimal wrong spot. Alright, but here's what we get. So we get about 23-ish, and that made sense. You know, that it's in the ballpark of the other two. This number probably isn't going to be the largest angle of my triangle. One of these probably is. It's actually probably this one. If you just make common sense of it, that's probably the obtuse angle there. Or it's the bigger angle. I shouldn't say it has to be obtuse. It has to be bigger than the 63. But just getting these numbers, hopefully they're in the same realm as the other ones. Question?
Are you gonna
Free
put
round?
this video on your website?
Yes.
For
So,
I have a
get a
question
lot
that
of
I looked at
views
your
of it?
website the other day, and your videos weren't very.
Lars, quit littering.
they're what?
Your videos weren't up to date.
Yeah.
Yeah.
I haven't updated it since the start of the quarter, so
Yeah.
it's been a while.
Mr. Ward! So I tried going on that night we did the homework.
Yeah.
French.
I got behind. So,
You were quite far behind.
My first language.
So I looked for, because I couldn't find the page number. I didn't have the page number written out of everything else.
I'm on the process of doing it.
Read
What?
it.
Mr. Ward, it's okay. We
All had it written down.
Okay. Question.
He got it written down.
All right, here we go.
First,
Oh, I got it.
I got it.
I love that term.
All right. Last step here, or last basic problem before we get to the new stuff today.
Fake news, actually. These Gots and
SSS postulates. Okay, now I know technically we had this earlier this week. We never did a problem with it, and I want to make sure that you know how to get to it. So this is the SSS postulate, which is where they give me 3 sides of my triangle. Again, I'm doing my very generic drawing. I'm going to make up some numbers here. Let's say this is 10, 9, and 15. Okay, now why this can be a triangle is because any 2 walls added to more in the 3rd wall, we have to double check that and make sure it is a triangle in the 1st place.
15.
All right.
But is 25 greater than 9?
That's awesome.
When you start this problem, I almost recommend that you go with these smaller angles first.
9.
Sometimes the book recommends you go with the larger obtuse angle. Going with the obtuse angle up here first, this angle, is that you have potential where it may not give you the right answer.
Because it could be negative.
It could be negative, and we could get an obtuse angle, not an acute angle. Because cosine, if we do log cosine, it won't tell me if it's obtuse or not. It always assumes that it's the smaller of the 2 triangles.
Why?
Because the way that you get negative numbers, it always tries to avoid negatives. Like when you do square roots, it always gives you the principal square root. That's what they're programmed for. It's always the positive answer. So when you're doing cosine, it will always assume the answers are positive, so it will never give you obtuse angles for it.
It'll just tell me.
Is there a different
It'll say-
mode that
yeah,
can set it to not do that?
Syntax.
Alright. If we're doing the math here, alright, if we're doing the math, the problem that I would do, I would always go after the smaller wall first. So I'm going to go after this, or this angle right here. I'm going to go after that one. The one that's across from the smaller wall. I don't know why, it's just the one that I always go to. So going after this one, it's going to be 9 squared equals, because again, this wall is by itself, it's always the wall that's across from your angle. That's technically the wall I would be finding in a normal case. Then it's the other 2 walls squared added together.
10,
So it kind of looks like the Pythagorean theorem. And then we have to add that little extra piece where you're subtracting that part where it's minus 2
times
times 10 times
15
15
times 9.
cosine the angle in between. And I don't have the angle that's in between. So it is potential where I could have an obtuse angle where the 15 is, and we'll see that later if it actually has a
Do
secondary
we have the
variable.
inverse cosine on
It shouldn't. It should have 1 second. So.
So,
Question?
will we have to end up doing the inverse cosine?
Yeah, we'll have to do the inverse cosine. Let's try to find the angle. Okay, doing the math here. 9 squared, this is 81. We have the 100. We have the 225. We have the 2 times 10 times 15,
20
which
times
is
30 is a big number.
It's at least 50.
300.
20 times 15. Wow, that was quick.
Okay.
300.
And then the next step. This is the part that people will go wrong. You
325.
gotta subtract these over,
Individual.
and that number you have to weight. That number's attached to cosine. Yeah, you have to divide by that number, because this is actually attached to cosine. You're not gonna add the 300 to the other side. Okay. Good. We're gonna subtract the 100 across, so 81, we're gonna subtract the 100. We'll subtract the 225. Okay. We have a negative 300 cosine x. To find the x, if I take, I'll get a negative number on the other side. So 81 minus 100 minus the 225, get a negative 244. So we get a negative 224. We divide the negative 300 across. So if you divide, you'll get a positive number. So 224.
0.813333.
I like the dice.
300.
Good call.
Say it again.
0.81
0.81.
3333.
0.81.
Good call.
And then we'll take the inverse cosine. Now here's how I know right here whether my angle is going to be obtuse or not. If this number on this side is negative, like somehow like this number was positive and you divided by a negative coming over, and it turned out to be negative over here for some reason, the answer that you're going to come up with won't be correct, because it should be technically a negative, it should be a negative number over here, and when you take the inverse cosine, it may not tell you the answer. It should be obtuse though, if you have a negative number over here. For mine, since it's positive, I know my answer is going to be, it's going to be acute. That's just something I should know. It's just one of those rules you'll get to learn over time. But you have to take the inverse cosine over. Question.
When you're doing this like generically, does it matter which number?
Like which angle you go after?
No. Well. Oh.
Wait, you have to chase the angles?
Because I'm just going after one of them.
So okay, whatever angle you go after, the opposite wall is the one that's on that other side of the
Yep.
Okay.
Yep. Yeah, good question. Okay, taking the inverse cosine of 0.81333333, blah blah blah, is 35 degrees. It's
0.9.
yeah, 35.557. It just depends. It actually depends on how many decimals are around it. Like if you didn't type as many threes as I did, it will go like a little bit more vague than that. So this is your first. Now that I have that one, I don't need to do the law of cosine again. So if I had to go after the other angles, I can just do the law of sine. You only have to do the law of cosine once in a problem. Everything else should be the law of sine, because law of sine is the easier of the two. You just do proportions and you solve it. All right, last thing today. Last thing. We have about 5 minutes here.
Oh
We're gonna learn about the Second Amendment.
No. Okay.
Can we try a geometry problem?
No. Hey, we need to. Yeah. We're going to talk about directional bearing. This is just one of the things that we need to see before we get to our project that we're going to kind of look at tomorrow.
Yes.
So hopefully you have it
It's
written
like an
down.
assembly project.
Mr. Ward, did you get my Second Amendment?
No.
Bare arms?
You're right to bear arms, I get it. Lars doesn't know how to.
That joke was well over my head.
It's like a hoodie.
He's saying that you're too smart for
You'll.
He can't comprehend.
Okay. Hey, we're good. Does everyone have this note on their paper?
You are Gucci.
Good. Okay. Moving on. Okay. Directional bearing. Here we go.
Is this what ships use?
All right.
Is this what ships use?
Yes.
They also use nautical miles per hour.
All right. Directional bearing.
the conversion?
Okay. If you don't know this term, directional bearing, it's using a compass, like an actual geographical compass for it, directional compass, so directional bearing. And the problem is with talking about directional bearing is that a lot of people get confused over the way it's set up. the actual compass itself, like that you're going to use for traveling, is pointing to magnetic north. And north is considered to be 0 degrees on directional bearing. So it's going towards, you know, the North Pole or very close to it. Now, the idea is that as you go around clockwise, the numbers get bigger. So eventually, when you go directly east, that's 90 degrees. And then when you go, you know, south, that's 180. If you go to the west,
270.
that's 270.
Yeah.
And then you're back to north. But if they say weird things like, they say east, or like, what do they say? They say
They come from
70 degrees southeast. Okay, so if they say 70 degrees southeast, whatever they say there, and again, they usually just write like this with no hyphen in the middle, that means you're going from south, you're going towards east 70 degrees like this. Okay, that's what they're actually talking about. That number going south, southeast 70, you start with the first letter, and then you go 70 degrees towards this one. So I'm going towards the east 70 degrees. Now, technically, that number is technically, it's like doing 110 degrees. So, doing directional bearing, they could say this. You're just going 110 degrees, and they could say it's, you know, 110 degrees east, you know, and you're just kind of rotating that direction. I've definitely seen it where the numbers that they have here, this is usually the most common when they do this, so they kind of give you a direction that they're going. But why this is important is because what ships do on the ocean is that they can't mark miles, right? Because all they see is the curvature of the earth. So what they keep track of is their actual speed. So if they start here, let's say this is port, wherever they're at, and they head off in a direction, they keep track on their compass what direction they're going and how long they're traveling. So they keep track on time. Because they know the speed of the boat, so the captain is constantly writing down, okay, they're going, let's say, and I'll put it in miles per hour, but they usually do knots. So let's say they're going 30 miles per hour, and knots it'd be, 24 or something like that. They'd be going so many knots per hour, and they know, okay, we traveled for 2 hours, and then suddenly we switch directions. Instead of going, maybe they're going east, southeast, where they're going like, maybe it's like 110 degrees. Let's go with the 110 idea. So this was north, so they're going this direction, kind of the east-southeast kind of direction, 110 degrees. And once they get here, maybe the captain makes a correction, and he goes, oh hey, now we're going to head south-southwest 50. Well, here's south, here's southwest, and this is 50 degrees. So he's going back this way to make sure that he can land on the correct direction, because maybe they are drifting. Well, the idea is that this time and the speed meant that I was going 60 miles, because you take 2 times 30. And that gives me how far I actually traveled. So why this is important is because now I'm starting to set up triangles.
Displacement.
I'm starting to set up triangles, and I can actually find where I'm going. So if I need to go back to port, because that's what all sea captains would have to know, is that wherever you landed, wherever you ended, you have to know exactly the bearing to get you back home. That's one of the trainings you take as a naval officer. Even if all technology fails, your watch shouldn't and a compass shouldn't.
What if your watch
So,
breaks?
no, because the watches they actually use, not going to break. They're flawless. They're not using they're using mechanical watches. They're not using they're not using any technology whatsoever. And there's a certain type of watch that they use that takes certain depth of water. They take certain amount of force, and it won't mess up the timing of it.
But what if it just got lost?
So it's probably not going to happen.
What if it did? Then how do you do it? You just
They would probably have to borrow from the other captains around them.
You go like this.
There's not more than one captain.
One person
That's like saying the United States has 10 presidents.
But then
Yeah, but there's only one on a boat.